Okay, now let's do some examples concerning the reliability. So far we've assumed that the reliability is fixed at 90%. There's a 10% chance of an individual bearing failing for the rated life. But now we're going to relax that a little bit. So here's our next question. Subjected to a radial load of 2,150 pounds, for how many revolutions is survival of these bearings guaranteed? Guaranteed. So we know that at a load of 2,150 pounds, then we will get 90% of these bearings surviving 1 million cycles. Life of L10, 1 million cycles. But for how many revolutions can we guarantee will 100% of the bearings survive? And for that we need a new equation. And this here is equation 11-8 in the 10th edition of Shigley. And what it's telling us is that the relative life for a fixed level of load, the relative life is given by this equation where R is the required reliability and these parameters x naught, theta, and b are given by a manufacturer. And different manufacturers give different parameters. We could plug these numbers from this manufacturer into here, and then we could figure out for that manufacturer what the relative life is. Now, we're going to assume that these bearings are made by manufacturer 2, and we're asking for how long will 100% of the bearings survive. So let's see what happens when we plug in a reliability of 100% into that equation from the previous slide. Okay, so this equation is going to tell us the relative life that we're going to get if we have a reliability of 100%, given that the bearing manufacturer is manufacturer 2, we know all the rest of these constants, and we can find out, again, we're talking about the fixed load, so it's 2,150 pounds in both cases, so we can just plug and chug in this case. So the reliability is equal to 100%, that's equal to 1. So that means this 1 over r then is going to equal 1, and this logarithm of 1 over r is the logarithm of 1. Remember that the logarithm means, well, basically, if it's base e, it's log base e is implicit, e to the whatever is on the right-hand side, whatever our answer is equal to 1. E to what equals 1? E to the 0 is equal to 1. So 0 is our answer here. So this whole term is 0. 0 to the 1 over b, that's going to be 0. Theta minus x naught, this is all going to be 0. This whole thing simplifies to whatever is over here, x naught. So the life, when the reliability is 100%, is equal to x naught. That's the meaning of this x naught parameter that's given by the manufacturers. The relative life is, in our case, for manufacturer 2, is 0.02. That means we are guaranteed to have a life at least 0.02 times the L10 life. So x being L over L10, we can find our actual life is equal to x times L10 is equal to 0.02 times 10 to the 6th cycles. We have 2 times 10 to the 4th cycles. That is the guaranteed life for this load. All right, I'm looking for a bearing that's going to support 1,000 pounds radial load for 10 to the 7th revolutions, and it needs to have a reliability of 99%. The gears are commercial off the shelf, and there's no impact involved. Is this ball bearing going to do the job? Well, because we have a lot of things changing, this is not the rated load, this is not the rated life, this is not the 10% or 90% reliability that we're used to. We're going to need actually one of the most general equations that we've got, and that is 11-9 in Shigley version edition, 10th edition. And here's the equation. It says that our rated load, or maybe the rated load that we need, is given by, well, this here is a constant here. It's called the load factor, and it depends on the conditions that we're operating in. These conditions over here have different load factors. This is the desired force that we want to, radial force that we apply in the bearing. We want it to be able to handle this much radial load for this much relative life, where A is equal to 3 for, we've seen this before, for deep groove ball bearings. and 3 1/3 for rollers. And then these here, x naught, theta, well, x naught again, and b, those are given by manufacturer. And finally, we've got the reliability that we're looking for. If we plug all that in, we're going to get what rated load we need to have or exceed in order for the bearing to meet our application. So this is kind of a combination of all the different things, reliability, the life, and the load that we want. And of course, if you knew what the rated load is, and you know what the reliability you need is, and you know one of these other things, say, then you can solve for the last one on the right-hand side, but it's usually written in this form here. And we just need it in this form here. We know what load we need to support. FD, in our case, is 1,000 pounds. We need it to last for 10 to the 7th revolutions. So XD is equal to the life we need over the L10 life. 10 to the 7th over 10 to the 6th is equal to 10 is our relative life. We need it to have a reliability of 99%. So RD, the desired reliability, is 99%, 0.99. Say we're still talking about manufacturer 2, so we can get our x naught, theta, and b right here. And the last thing we need is this load factor, and that's what I provided this information here for. It says the gears in the machine are commercial off the shelf. We've got commercial gearing. That suggests a load factor of 1.1 to 1.3. It says machinery that has no impact, 1.0 to 1.2. Let's use a factor of 1.2 to be kind of in the middle of this sort of range of commercial gearing. So let's say AF is 1.2. And then we could use the equation to find out what rated load we need. So 1.2 times 1,000 pounds. All this times we need a rated life of 10. That is over 0.02 plus 4.459. That is going to get multiplied by the logarithm of 1 over 0.99 to the 1 over 1.483. And this all goes to the 1/3 power. So let's go ahead and simplify this. This is going to be 4.439. If we write that a little bit more compactly, I think that we can fit all this on the same line. Now let's see, 1 over 0.99, that's 1.01 repeating. So that the log of that 1.01 repeating, that log is 0.01005. Now take that to the 1 over 1.483. I'm getting 0.04496. And I suggest that you go through those steps and simplify that bit before plugging the rest into your calculator, because otherwise it can get a little hairy. Doing the rest of the calculation myself, I'm getting that we need a rated load of 4,285.26 pounds. That is the rated load we need to handle the 1,000 pounds at 99% reliability for a longer time. And so will this ball bearing do the job? The ball bearing that we were considering, we've been using the same one the whole time, had a C10 of 2150 pounds force. And so we need something that's stronger than that. This ball bearing is not going to do the job.